Now that you know a few maximum power point tracking methods, let's take a step back and see how these methods compare to each other. In this video, I will explain how these methods differ in complexity and therefore cost. They also differ in terms of accuracy as well. However, before we get any further, I want to talk about the major drawback of maximum power point trackers that I haven't mentioned yet. As you know, an MPPT tries to find the maximum power point voltage VMPP. You have seen both direct and indirect ways to accomplish this. For direct methods, we can use different ways to scan the IV curve of the solar cell and find the maximum power point. However, we have been using one major assumption, which is that the solar panel setup we are using has an IV characteristic of a normal solar cell. This may not always be the case. Here you can see an IV and PV curve of a solar array that is partially shaded. You've seen how the curves come to be during the videos on solar modules. What is interesting in terms of maximum power point tracking is that this results in a curve with different local maxima. If you are using a power point tracking technique such as the perturb and observe or incremental conductance, you may end up at a local maximum rather than a global maximum. You can see that this could result in a significant decrease in power output. In order to overcome this problem, you would need a full scan of the PV curve. SMA, a leading company in inverter design, uses a proprietary technique called the OptiTrack Global Peak. You can learn about it by following this link here. Okay, now let's compare some of these techniques side by side. We will be looking at some simulations and measurements that were carried out by Holm and Rope in 2000 on these techniques. You will see a percentage in these results, and this percentage determines what percent of the potential energy was produced by each technique throughout a sample period of time. So 100% here would mean that the solar array was operating at the maximum power point the entire time. Here you can see the results of the work of Holm and Rope. Here, P and O stands for perturb and observe, INC stands for incremental conductance, and CV stands for constant voltage. Things to note here is that both a perturb and observe and incremental conductance outperform the constant voltage method. This is likely due to the inaccuracy of the constant voltage method at low irradiances. They conclude in the paper that though incremental conductance slightly outperforms perturb and observe, it is not worth it due to the increased complexity of the execution of the method. Here we see a comparison of the different techniques. On the x-axis, we have the cost of a certain technique, and on the y-axis, we have how much energy is generated. Here you can recognize IC as the incremental conductance, P and O as the perturb and observe, CV as the constant voltage, and OV as the fractional open circuit voltage method. You can see again that the incremental conductance technique does marginally outperform the perturb and observe technique, but is significantly more costly. However, cost and efficiency are not the only two metrics to be concerned with. I will also link the paper of Esrom et al. That compares many different techniques among a slew of different metrics. Going through everything here is outside the scope of this course, but feel free to study more with the attached materials if you wish to go further into maximum power point tracking. Now, before I finish up with the topic of MPPT, I want to show you how this technique is actually achieved. Before we do that, let's recall what we need to do to maximum power point track. We need to find out what the VMPP of the solar array is. Then we need to isolate the voltage from the solar array from the voltage of the load so that the load has its desired voltage and the solar array operates at VMPP. We will do this using a power electronic device. This device is known as a buck-boost DC-DC converter. I won't go through how the DC-DC converter operates, but I will point your attention to a few important aspects of it. First, you'll notice that there is a VI representing the input voltage and a VO representing the output voltage. This output voltage is over a load, while the input voltage is generated by a source. Finally, you will see that there is a switch labeled S. So you can imagine that we have a given output voltage and we want to force the input voltage to be our desired VMPP. If we know VO and we know VMPP, we can achieve this by switching S on and off in a controlled way. You will learn all about how to design this DC-DC converter and how to control S later in this course. For now, just realize that a DC-DC converter with an intelligent switch is the mechanism used to achieve maximum power point tracking. Usually, this MPPT is implemented in one of two components in the PV system design. It is either in the charge controller, which is shown here in black, or the inverter, which is shown here in yellow and gray. There usually isn't a separate component that is just responsible for the MPPT. The MPPT logic is hard-coded into one of these devices. So if you want to use a specific MPPT algorithm, you will have to check the manufacturer of your charge controller or inverter. This ends the video series on maximum power point tracking. Through these videos, you have learned why we use MPPT, some algorithms for MPPT, and an overview on how to select a given MPPT depending on whether you are interested in cost or maximum efficiency. Finally, you learned that MPPTs are achieved using DC-DC converters, which are hard-coded into charge controllers or inverters. I hope you've enjoyed learning about maximum power point tracking.